Hello, I'm Carlos Roswen. This is the CRS channel. I'm going to continue with physics problems in kinematics. I'm going to continue with problem 8. Here I want to make a rectification as to the use of these formulas for the calculation of the velocity and the calculation of the position. In the case of the velocity, these ti1 minus ti's are selected points respectively. What do I mean by this? Here the data points for the given data for the values of the acceleration are given by the starting points and end points for the intervals shown in the graph here. But if the values of velocity and position are to be calculated, we have to take points within the intervals. So this is the data used for the time values for the time intervals from 0 to 40 seconds. Based on these time values, I used these formulas to calculate the velocity and the position. So this, for example, could be a ti. This could be a ti plus 1, and so forth down the column. So that using this formula and remembering what were the respective values for the acceleration, so I used this formula to obtain the values of the velocity for these time values. Here we can see the respective formula used in the spreadsheet to obtain the values for the velocities. So this would be the velocity of the previous value of velocity, and this would be the value of the acceleration used corresponding to the respective interval. The interval is shown here. And this would be the time difference, the I plus 1 value minus the I value. And in this way, continuing down the column, one would obtain the respective values of velocity. Now, this formula was used when we had non-zero acceleration. When the acceleration was 0, we already knew that the velocity had to be constant, and when the acceleration changed again, as here, we would use this formula again. Of course, if you can see that if acceleration is 0, then that means that v of ti plus 1 equals v of ti. The same was done for the position. Only that for the position, we would normally use the formula for the areas of trapezoids in which the height of the trapezoid is ti plus 1 minus ti, and the two bases would be v height plus 1 and vi. And remembering that the area of the trapezoid is 1/2 of the height times the sum of the two bases, well then, using that formula, we can obtain the area for each of the respective trapezoids for a determined interval. So that was done here, especially when the velocity changed. So when the velocity changed, we could use this formula as it appears here. We have the 1/2. This is the sum of the bases. The g's correspond to the respective values of velocity. This is the height, that is the time difference for each of the, let's call them subintervals of ti plus 1 minus ti. This would be the previous value for position. And you would go on and on for the rest of the column. And in that way, we would obtain for the position this graph, which corresponds to a curve. Here we have, for the case in which we have constant acceleration but different from 0, we have this parabolic type of curve. For the part where the acceleration was 0 and we had a constant velocity and we have a line, here we have again acceleration different from 0, and then we have the parabolic curve again. Here we have constant velocity, and here we have the straight line again, and then here we have the parabolic curve for the last interval for which the acceleration is different from 0. So here we have for the first interval, we have that the velocity can be expressed as v equals to t. For the second interval, we have constant velocity 10, v equals 10 meters per second. For the third interval, we have v equals minus 2t plus 40. For the fourth interval, we have v equals minus 10 meters per second. And for interval 5, we have v equals 2t minus 80 meters per second. For the position, we have then that for interval 1, we have x equals t squared. For interval 2, we have x equals 10t minus 25. For interval 3, we have minus t squared plus 40t minus 250. For the fourth interval, we have minus 10t plus 375. And for the fifth interval, we have t squared minus 80t plus 1 plus 1600. Okay, so these equations here were obtained by simple use of the known equations for motion and that correspond to the respective type of motion for each of the intervals. For constant velocity, you know that, for constant acceleration, interval 1, we know that since v0 here was 0, then we have that v equals at. Here the velocity is constant. Here we know that v equals minus acceleration times, here we have t minus the initial value of time for the respective interval. In this case, for interval 3, initial value was 15 plus the initial velocity for interval 3, that was 10 meters per second. Simplifying, we get then that we have minus 2t plus 40. Again, we have for interval 4, we have constant velocity, that's minus 10. And for interval 5, again, we have the acceleration times the time at, so that's 2t. And we have, as with interval 3, you have to take the beginning time of the interval as 35, so this is actually 2 times t minus 35 plus minus t minus 10 meters per second, and simplifying we get 2t minus 80. Adopting the same procedure here, that's the way we obtain these equations for the position. Remembering the formula of x equals 1/2 of at squared plus v0t plus x0, applying that for each one of the intervals, and remembering that t is actually replaced by t minus t0, where t0 would be the starting point for each interval. Okay, now we will go to the next problem in the next video.